Hi all, welcome to another video of linear control system based on the KTU syllabus. And today we are going to discuss about the Nyquist stability criterion, that is from the 6th module of linear control system. So this video is basically prepared for answering a question for 7 or 8 marks if asked in the university question paper. And if the question is just for a 5 mark, you have to answer, you have to take the main points from this video for answering the question. Okay, so let's start the explanation of Nyquist stability criterion. So initially we are considering a function f of s. Okay, that is, we know the f of s, we can represent the function f of s as s minus zn into s minus z2 up to s minus zn, and divided by s minus p1 into s minus p2 up to s minus pn, where these roots of the numerator part denote the zeros and the roots of the denominator part denotes the poles of the system. Okay, so here the function has m number of poles and m number of zeros and n number of poles. So here s is a complex variable, that is normally whether it is a pole or a zero, normally we can express s as a complex variable, that is s is equal to sigma plus j omega, that we know. Normally we are plotting that poles and zeros in the s plane with the real and imaginary axis are sigma and j omega, that is sigma is the real part and omega is the imaginary part. Okay, and for a particular value of sigma and omega, the s will represent a point in s plane. So s is a complex variable. So since s is a complex variable, the function f of s will be also a complex quantity for any value of s. Okay, that is, this entire function f of s is also a complex variable. Okay, because s is a complex variable, so we can express f of s as u plus jv. Okay, and another variable f of s as u plus jv, where u is the real part of f of s and v is the imaginary part of f of s. So let us define another complex plane called f of s plane here. Okay, f of s plane. So from the s plane we have derived an f of s plane with the axis as x-axis as u and y-axis as jv. Okay, so a new plane we have developed, f of s plane. So which means for every point in s plane we will have a corresponding point in f of s plane. Okay, so we can also say like that, that is, for a contour in the s plane there exists a corresponding contour in f of s plane. So this is the s plane. We know that for s plane that's a sigma and j omega, real and imaginary part. Okay, so if this is a contour in s plane, then there exists a corresponding contour in f of s plane also with axis u and jv. Okay, so that is the concept. So this contour is nothing but there is a possibility of zeros and poles in this contour. Okay, zeros and poles. So here we can consider a function, that is f of s. We can consider any function, and this function is having two zeros. Okay, that is z1, two complex zeros, z1 and z2 in the right half of s plane. And if you are plotting the corresponding contour in f of s plane, okay, f of s plane, so this contour is actually it is a chance for the existence of any poles and zeros here. So here actually this function has two zeros. Okay, two zeros, and if you are plotting the contour in f of s plane, the figure is like this. So by observing this figure, we can find a relationship between these two figures. Okay, that is, here we are having two zeros on the right half of s plane. So here we can see two clockwise encirclement. Listen carefully. Two clockwise encirclement of origin in f of s plane. So which means here there are two zeros on the right half of s plane. So here two clockwise encirclement we could see. Okay, so from that we can will get a relationship between the s plane and f of s plane contour. Okay, so some assumptions are there based on that. That is, if s plane closed contour encloses z number of zeros in the right half of s plane, then the corresponding contour in f of s plane will encircle the origin of f of s plane z times in the clockwise direction. So in the previous case, we are having two zeros on the right half of s plane, which means the corresponding contour in the f of s plane is having two clockwise encirclement in the f of s plane. Okay, and instead of these zeros, if poles are existing, okay, so if s plane closed contour encloses p number of poles in the right half of s plane, then the corresponding contour in f of s plane will encircle the origin of f of s plane p times in anti-clockwise direction. So instead of this clockwise direction, if you are having poles, okay, if you are having two poles in this right half of s plane, we are having two anti-clockwise encirclement. Okay, two anti-clockwise encirclement of this origin. Okay, two anti-clockwise encirclement. So anti-clockwise encirclement is like that. That is, okay, in this direction we are having two anti-clockwise encirclements. Okay, so that is the second point here. And if the s plane closed contour encloses z zeros and p poles, okay, z zeros and p poles in the right half of s plane, and if p is greater than z, okay, that is, if you are having for example, if you are having z is equal to 1 and p is equal to 3, so p is greater than z, okay, then the corresponding contour in f of s plane will encircle the origin of f of s plane p minus z times in the anti-clockwise direction. So p minus z, that is 3 minus 1 is 2. So here the number of poles is higher. Okay, number of poles is higher. So corresponding to this pole, we know that if poles are existing, anti-clockwise encirclement will be there. Okay, so here if p is greater than z, that is 3 is greater than 1. So p minus z times, that is 2 times 3 minus 1, 2 times the origin of f of s plane will encircle by 2 times in the anti-clockwise direction. Okay, the corresponding contour in f of s plane will encircle the origin of f of s plane p minus z times. So here in this case 2 times in anti-clockwise direction. Okay, because here the number of poles is higher, so the corresponding term, that is anti-clockwise, will dominate here. Okay, so anti-clockwise direction we will have a encirclement. Okay, encirclement there. And if the reverses, if the condition reverses, okay, that is if z is greater than p, so z minus p times in the clockwise direction, that is zeros are higher, so corresponding to 0 we are having clockwise direction. So z minus p times in the clockwise direction, we are having encirclement in f of s plane. Okay, and the remaining points are, if s plane closed contour encloses z zeros and p poles in right half of s plane, and if p is equal to z, that is number of poles equal to number of z, then the corresponding contour in f of s plane will not encircle the origin of f of s plane. Okay, if both the poles and zeros are equal, the corresponding contour in f of s plane will not encircle the origin of f of s plane. Then the closed contour in f of s plane may be like that. Okay, maybe like that in any direction. It will not encircle the origin here. Okay, the closed contour may be like that. Okay, so it will be more clear if we are discussing the problems, so we can see the problem in the next video. And one more point is also that if the S-plane closed contour does not enclose any poles or zero, then the corresponding contour in f of s plane will not encircle the origin of f of s plane. And one more point. Okay, and mathematically we can express the difference of p and z as n here. N is the encirclement of origin of f of s plane, and z is the number of zeros of f of s lying on the right half of s plane, and p is the number of poles of f of s lying on the right half of s plane. Okay, so from this we can make three assumptions based on the value of n. Okay, so here is an example of that number of poles is equal to 2 and z is equal to 1. So 2 minus 1, 1. So one encirclement will be there in the f of s plane in the anti-clockwise direction because poles are dominating. So here we can see an example. Okay, so from this, based on the value of n, we are having three assumptions. That is, if n is positive, that is, if n is positive means p minus z, it is equal to n. Okay, that is if poles are higher. Okay, poles are higher, that is n is positive, then the direction of encirclement of origin f of s plane will be anti-clockwise. And if n is 0, then there will be no encirclement of origin of f of s plane. And if n is negative, then direction of encirclement of origin of f of s plane will be clockwise. Okay, so three assumptions are made. Okay, and we are mainly going into the Nyquist stability criterion. So according to my opinion, if the question asked for a 5-mark question, you can answer from this point also. Okay, from this point itself. That is, here we are considering a closed loop transfer function of c of s by r of s as g of s by 1 plus g of s into h of s. Okay, and we know that the characteristic equation is 1 plus g of s into h of s equals 0. Okay, so here we are considering it as f of s. Okay, so initially we were considering f of s as s minus z into s minus z2 something divided by s minus p1 into s minus p2 in the first starting of this video you are seen. So here we are considering the function f of s as 1 plus g of s into h of s. That is the characteristic equation of our closed loop transfer function. Okay, so based on this value of f of s, we can say, okay, we can state the Nyquist stability criterion. Okay, and we know that the loop transfer function g of s into h of s can be expressed as, that is g of s into h of s, that is g of s into h of s is expressed as 1 plus g of s into h of s minus 1. That is, we are adding and subtracting a 1 here, and this 1 plus g of s into h of s is f of s. Okay, this is f of s. So here we are substituting it as f of s minus 1. So from this equation, it can be concluded that the contour of f of s drawn with respect to origin of f of s plane is same as the contour of f of s minus 1 drawn with respect to minus 1 plus j0 of f of s plane. Okay, that is, in the previous slides we have learned the encirclement of contour, that is the f of s plane contour with the origin. Okay, but here we are making a new assumption that is, here the g of s into h of s is expressed as f of s minus 1. Okay, so it can be concluded that the contour of f of s, okay, the contour of f of s drawn with respect to origin. In the previous cases we have drawn the contour of f of s with respect to origin, okay, of f of s plane is same as the contour of f of s minus 1. Okay, the contour of f of s minus 1 drawn with respect to minus 1 plus j0 of f of s plane. Okay, thus the encirclement of the origin of f of s plane by the contour of f of s is equivalent to the encirclement of the point minus 1 plus j0 by the contour f of s minus 1. So here we can see the statement here. Okay, that is, this is the f of s plane. Okay, this is the f of s plane. So here we are considering the encirclement of origin. This is the origin. Okay, so this is same as if you are considering the encirclement of minus 1 plus j0 point. This is minus 1 plus j0 point of contour f of s minus 1. Okay, this is f of s minus 1. Okay, so both concepts are same. Okay, that is actually stated in this slide. Okay, so here f of s is 1 plus g of s into h of s. So we are writing that g of s into h of s as a function of f of s. Okay, that is g of s into h of s as f of s minus 1. Okay, so instead of plotting this f of s, that is, instead of plotting this 1 plus g of s into h of s, it is enough to plot this g of s into h of s alone. That is f of s minus 1. We are plotting this f of s minus 1, and we are observing the point minus 1 plus j0, the encirclement of minus 1 plus j0 point. Okay, so actually the Nyquist stability criterion can be stated as, this is the actual statement of this Nyquist stability criterion. Okay, so if the g of s into h of s contour in the g of s into h of s plane, so here we are considering g of s into h of s plane only, that is f of s minus 1 plane we are considering. Instead of this f of s, instead of this 1 plus g of s into h of s plane, we are considering g of s into h of s contour only. Okay, it will be more simple. Okay, that's why we are considering. So if the g of s into h of s contour in the g of s into h of s plane, that is f of s minus 1 plane, corresponding to Nyquist contour in the s plane, encircles the point minus 1 plus j0 in the anti-clockwise direction as many times as the number of right of s plane poles of g of s into h of s, then the closed loop system is stable. Okay, that is, it is the stability constraint here. That is, if you are having for example, if you are having two number of right half of s plane poles of g of s into h of s, that is, this f of s minus 1 function is having two poles on right half of s plane. Okay, and if after that we have drawn the corresponding f of s minus 1 contour in the f of s plane. Okay, that is g of s into h of s contour. So in that we have observed that the contour have encircled minus 1 plus j0 point two times in the anti-clockwise direction. Okay, then we can say that the system is stable. Okay, if these both the values are not equal, then the system will be unstable. Okay, that is, if you are having two poles, two right half poles here, that is of g of s into h of s, we are having two right half of poles in s plane. Okay, in s plane, and if you are drawing a corresponding contour in f of s minus 1 okay, that is, if f of s minus 1 contour if you are drawing and if we are having only one encirclement of minus 1 plus j0 points in anti-clockwise direction, then the system will be unstable, because we are having two poles in the right half of s plane and we are having only one encirclement, anti-clockwise encirclement of minus 1 plus j0. Okay, so the system will be unstable. So this is the stability constraint, and we can make three assumptions based on that. Okay, based on the statement, that is, first one is no encirclement of minus 1 plus j0 point. So this implies that the system is stable. That is, if the f of s minus 1 contour is not encircled the point minus 1 plus j0, this implies that the system is stable if there are no poles of g of s into h of s in the right half of s plane. That is, if you are not having any poles on the right half of s plane, then the system will be stable. And if we are having poles on right half of s plane and we are the corresponding contour is not encircle the point minus 1 plus j0, then the system will be unstable. Okay, this is the first point. Then the second point is anti-clockwise encirclement of minus 1 plus j0 point. So in this case, the system is stable if the number of anti-clockwise encirclement is same as the number of poles of g of s and h of s in S-plane. Okay, that is, if you are having two poles, okay, if you are having two poles, right of poles in S-plane, and we are having two encirclement of minus 1 plus j0 point in anti-clockwise direction, then the system will be stable. Okay, if the number of anti-clockwise encirclement is not equal to number of poles on right of S-plane, system will be unstable. And one more case is there, that is clockwise encirclement. That is, instead of this anti-clockwise encirclement, if you are having clockwise encirclement of the minus 1 plus j0 point, so in this case the system is always unstable. Okay, always system will be unstable, but we can make some assumptions based on that. That is, if there are no poles of g of s and h of s in right of our S-plane, that is, if you are plotting the poles on S-plane, we are not having any poles. Okay, we are not having any poles in right of our S-plane, then the number of clockwise encirclement is equal to number of poles of closed loop system on right of our S-plane. Closed loop system, that is, closed loop system is C of s by R of s. Okay, that is g of s by 1 plus g of s into h of s. Okay, that is our closed loop system. Okay, so if there are no poles of g of s into h of s in S-plane, okay, but we are having a clockwise encirclement of minus 1 plus j0, okay, then this clockwise encirclement, that is the number of clockwise encirclements, will give, okay, will equal to the number of poles of closed loop system on right half of S-plane. Okay, so actually that is the assumptions made from this Nyquist stability criterion. Okay, so this statement and this assumption, three assumptions, are very very important, and also don't forget to draw this figure also. Okay, so I think it's very much enough for a 5-mark question. Okay, so I hope all of you understand the concept well. So thank you.